Today's lesson will be on the periodic trends that are found in the periodic table. Like we studied in previous classes, the periodic table has been arranged in a certain order of increasing atomic number. When it's ordered this way, that the elements have similar properties, like the elements in a family, which are the ones that go down a column here, they have similar properties. Um, Also, when you arrange them this way, you will find that there's this gradual change as you're going across the periodic table. Okay, so and then when you move, when you go across a period here, there's this gradual change, but then when you go to the next period here, you'll see that same gradual change happening again as well. Here is we're going to look at what do we notice structurally as we're going across a period, and what are we noticing as we are going down a family. Okay, so you can pause the video and brainstorm what items you see here. Okay, so as you're going across the row here, or going across the period, so for example, if we're looking at the lithium all the way to the neon row here, what we're noticing here is that the electrons are increasing as we go across, okay? The protons are increasing as we go across. The neutrons don't have that so much of a pattern. Sometimes they're the same, sometimes, generally they are increasing them, okay? But what I want you to focus on here are the protons and electrons today. So as these electrons are increasing, the number of them, they are filling the same shell. So if you see here, you have your nucleus, and then you have the first electron shell, and then you have the second electron shell. So again, just wanted to note that this is not the way I want you to be drawing the Bohr-Rutherford diagrams. Remember, if there's two, there should be one up here, one down here, okay? But this is just a nice visual that I found so you can kind of quickly see the electrons increasing. Okay, so again, same electron shell is being filled, same the second one, and the protons are increasing by one, right? 3, 4, 5, 6, 7, 8, 9, 10, and the electrons are also increasing by one. Okay, so now if we are going down a column here, okay, or down a family, what are we noticing here? So we are noticing the protons increasing quite a bit, so like in a 2, 8, 8 pattern so far with what we have here. We're also noticing the protons are increasing, the electrons are increasing, but we're also noticing the big thing here is that as you go down, you gain an electron shell or an energy level. So hydrogen has 1, right? The rings here, lithium has 2, sodium has 3, potassium has 4. So as you go down, there are more and more energy rings or electron shells, okay? Places where the electrons are going. Okay, so there are a lot of different trends in the periodic table. We are going to concentrate on two of them today. The first one is atomic radius, and the second one will be ionization energy. So the atomic radius is the distance from the nucleus, okay, so that's the center here, to the very outside electron shell, okay, or where the valence electrons are. So like if you're looking at the different elements here, they have these measurements here, and then here's more of a visual diagram of going from the nucleus right to the outside energy shell, and they're just using different units here. And then ionization energy, that's the minimum amount of energy required to remove the the valence electron off a neutral atom. Okay, and so here's another visual here. So we're just removing, again, this diagram's not correct, but just kind of just see the visual. We're removing an electron. Okay, and that takes the energy, so that's what that energy is, the ionization energy. Okay, so the energy to change it to an ion. So from our previous investigation the other day, where we were graphing so atomic radius data and ionization data, we found overall, it's not perfect, but in general, the atomic radius was increasing as we went this way, going backwards, I guess, on the period, or going from right to left, and then going down in the periodic table, the atomic radius was increasing, getting bigger and bigger. And then the ionization energy was increasing as you go up a family and then increasing as you went across the period. So again, we graph the data here, and so the red here is the ionization energy, and here is the atomic radius. So yeah, so to match that up, you can see how as we go across the period here, we so if we were going this way, it was decreasing, okay? But I wanted to have some diagrams that you can memorize where it was always just like in which direction is it increasing. And then, so some of you also noticed that the atomic radius increased dramatically every time you started a new row. So like you kind of be, as we go across the period, it was decreasing, but then as you go into the next period, it would bump up. Okay, so big increase and then gradually go down again. So up and then down. Okay, the ionization energy, we saw the opposite. So we were seeing an increase as we were going across the periodic table, but then when we went to the next group, there'd be a big drop. Okay, and then, but in general, most of you concluded that the atomic radius, right? If it were going up, it would be decreasing, and going across, it would be decreasing, right? But the ionization energy, as you go up, is increasing, and going across, increasing. So they're opposite of each other. So with today's lesson, we're going to carry on with what we found in this investigation and be able to explain why is this happening. So, okay, so because we graphed the data and we found that, it was increasing this way, it was decreasing that way, but we want to explain now why is this happening, okay? Why do we see this trend? All right, so in order to study that, we need to kind of go back and look at what electrostatic forces are. So in general, in earlier years in science, you learned when you take a positive and positive, they will repel each other. If negative, negative, they will repel. So the same charges will repel each other. But if they're opposite charges, they will attract. Okay, so so electrostatic forces are the attractive or the repulsive force between electrically charged objects. Okay, so now we know which way the charges are going. So like we're going to have a proton, which is positive, and an electron, which is negative. So we're going to be studying the attraction between those, okay? So the strength of the electrostatic force between the proton and electron will depend on the size of the electric charge. So basically how many charges are there, okay? And it'll also depend on the distance, like how far apart are they. So here we'll just look at some visuals here. So if it's based on the charge, so if you have more charges involved, you're going to have a greater attraction force. So it's almost like if you have several magnets, it's a lot stronger than just having the one magnet. Okay. If you just have one charge, one positive, one negative, or just like you think of it as this is the fewer one, this one has more, you're going to be weaker, the weaker attraction force, okay? Where this was going to be a lot stronger. I know it looks like the arrows are going outwards, but think of these as going towards each other. All right, and if it's if there's a distance between, like a difference in distance, like this one was a difference in how many charges there were. If there's a difference in distance, same thing. That's going to affect how well they can attract. So the closer you are, the greater the force will be. The further you are, the weaker it will be. Okay, so you can kind of look at these balloons as well. So maybe you rub them on your head and you charge them, and then when they're closer, the attraction force is greater, okay? When they're further apart, it's harder for them to attract each other. Okay, and then just to note that if you are kind of looking at how, I guess the difference in the charge and the distance here, because they do both affect the force of attraction here. The distance, like when that changes, there will be a much more significant change in the force of attraction compared to, just adding a few more positives and adding a few more negatives and so forth. Okay, so yeah, so when you get further away, it's a pretty big difference in the force of attraction, where if you were just changing from like 1 to 2 charges to 3 charges, the attraction force isn't as much. All right, so now that we have kind of an intro or a review of the electrostatic forces, and then kind of looking at what was happening with atomic radius and ionization energy. Let's go into structurally why this is happening, okay? Why are these trends being seen? Okay, so as we move left to right across a period, right? What are we noticing? So I'm looking at the example of lithium to neon here again. So what we're noticing here is that, remember, that it was the same shell, okay? So same electron shell, energy level, same ring, whatever will help you remember it, is being filled with the more and more electrons, right? The nucleus here has more and more protons in it. So if we're looking at just the protons first, we're noticing that, yeah, they increase by 1 proton as we go across the period. So you want to look at, so with that increase, you're going to get an increase in the attraction with the electrons. So we call this the effective nuclear charge. So just think of it as kind of like the little power of the nucleus, okay? So the effective nuclear charge, ENC, is the overall force of attraction between the electron and the nucleus, okay? All right, so as we're going through, okay, across the period, so we do have the electrons increasing, but really they are just going on to the same ring. That ring is essentially the same distance. It's not perfect, but it's pretty much the same distance from the nucleus. So these electrons are going into a spot here, but what's happening as we go across the table, the protons are increasing, okay? So therefore the force of attraction is increasing. So with the effective nuclear charge, you can see here, we can kind of put a numerical value on these different atoms here. So think of this one as lithium as +1, but then as you go across, this one adds a proton so to the nucleus. So this is the first one. This one is +2, so it's more powerful, right? So it's better at attracting those electrons. So this one will be +3, +4, etc., right? So as you're going across, you're increasing the number of protons, and so you're increasing the effective nuclear charge. So the greater the effective nuclear charge, the better that you're going to be able to attract those electrons in. Okay, so in that case there, what's happening with the atomic radius? Well, it's decreasing because it's pulling and pulling those electrons in. What's happening with the ionization energy? Well, it's getting harder and harder to pull those electrons off because the nucleus is getting better and better at keeping those electrons close to itself. So, and then just a reminder here, same electron shells being used here, okay? So we're just filling into the same ring, so really they're the same distance, so it's distance isn't affecting the force of attraction here, it's the effective nuclear charge as we go across the period. All right, so what's happening when you go down a family here? So down the periodic table. So we're looking at hydrogen, the first group here, hydrogen down to potassium here. Again, you are getting the same, effective nuclear charge increasing as we go down, right? So you have like 1 proton, 3 protons, 11 protons, 19 protons. So you're getting this big jump and increase of the effective nuclear charge. But what else are you noticing here? If you look here, the electron shells are increasing. So here hydrogen has 1, lithium has 2. So as we keep dropping down, we get another one, 3 for sodium, 4 for potassium, right? 1, 2, 3, 4. So as we go down, we're increasing the number of shells, and therefore we're increasing the distance that the nucleus is from its electrons, so especially the valence electrons. So so as we go down, because the distance is increasing, where the force of attraction between the protons and electrons are decreasing, okay? So again, like I showed you, we were talking about before, distance has a bigger effect on changing that force of attraction, okay? And the reason why here is that as we go down, we get more and more energy levels, right? So if I keep saying energy levels, I mean those electron shells. And then, so if you're getting further and further away from the nucleus, so being able to attract those electrons in, it's becoming harder and harder because in a way it's getting bigger and bigger. It's still a really tiny piece of matter, but it's just it's getting further and further away, okay? But there are other factors that come into play here as well. So as you go down, see how you're getting more and more electrons? like if we're looking at like all of them have one electron on the outside, right? But as we go down, the inside shells here have more and more electrons. So as you get more and more electrons, you're going to get, because we saw that electrons, right, are both negative, right? So we get that negative repulsion happening, right? So what's going to happen here is that very outside electron is going to be pushed away. So how does that relate to the atomic radius and the ionization energy? Well, as you go down, because there's more and more shells, you're getting a greater distance from the nucleus, so therefore your atomic radius is increasing as you go down, okay? All right, but what's happening with the ionization energy? Well, as you go down, the ionization energy, it's getting easier and easier to rip off this electron, right? So think of it as, we want to remove this electron, well, um, hydrogen's going to hold on pretty tight because it's pretty it's pretty close to the nucleus, right? But then lithium, this electron's further away because it has another energy shell. Okay, sodium even further. Potassium, it's like, here, just take it because I've got all these other electrons here that are shielding me from holding on to that electron. So yeah, as you go down, the ionization energy is less, right? It takes a lot less effort to take off the electron, okay? But as you get more and more electrons and energy shells, you will get bigger and bigger as the radius. Okay, so if we're, let's just recap here to look back at the atomic radius again. That's the distance from the nucleus to the very outside electron shell here. So we found in our investigations that the general trend was when you went this way and this way, it would increase. Okay, the atomic radius increased. So going right to left or going down a family, the atomic radius increases. So again, there's just little blips here and there, but in general, that's what's happening here, okay? All right, so again, if you wanted to match just kind of all the ideas above and get them on written down. So as you go left to right, so what we're noticing as we go this way, we're noticing more and more protons, more and more electrons, right? But then it all comes down to the effective nuclear charge is increasing as you go this way across the table. So if that is increasing, the force of attraction between the protons and electrons are increasing. So it's like a magnet, you're pulling those electrons in, and therefore your radius will decrease, right, as you go that way. So I just like to memorize it as which way is it increasing, so that's why I show the arrow this way. But I know when we're looking at this, we're like, oh, what's happening as we go across the period? Well, it's decreasing. Okay, what if we're going down a group? So again, what's happening here is that we have more and more rings here, and so you will have kind of the shielding effect happening here, right? So you're going to find that the nucleus is getting further and further away from those valence electrons, so you can't pull those electrons in as well. Okay, so as you go down, you're going to find that the distance is increasing, so therefore the radius will increase. And with the ionization energy, we found the trend was that as you went up and this way, so it's the opposite of the atomic radius, the ionization energy was increasing when you go up the family and across the period. Okay, so again, what is this? This is the energy required to remove that one electron off the atom, okay? All right, so you saw the pictures here, and here's kind of some numerical data here. You'll see as you go across, it's increasing. As you go up, it's increasing. Okay, so why is that happening? So if we're looking here again at the structure, as you go across the period, the effective nuclear charge is increasing, right? So the attraction between the protons and electrons are increasing. So if that is increasing more and more as you go left or right, if you try to rip off an electron now, it's becoming more and more difficult and you need more energy. So therefore the ionization energy increases as you go this way across the table. Okay, and if you go down, what is happening here? So again, the effective nuclear charge is increasing, but what's happening here that's greater than that is that the distance away from the nucleus is increasing. So from the nucleus out to the outer shell here, because as you go down the periodic table, you get more electrons, so you need to have more energy shells. So as you go down, increasing the number of energy shells, electron shells here, increases the radius, all right, of the atom, right, the element. So if you are increasing that distance away from the nucleus, the nucleus is not going to be able to hold on to those electrons as well. So that's why as you go down, the ionization energy decreases. It takes less energy to remove these electrons. Okay. All right, so that, yeah, hopefully you feel confident now, being able to use the terminology of effective nuclear radius, nuclear charge. Okay, so be able to use that in your description when you're going across a period. Okay, it is also happening down a period, but it's not as significant. What's more important as you go down is the whole shielding effect of how in the distance, right? It's a shielding effect in distance. Okay, so the distance is increasing as you go down the family, and therefore that's what affects the radius and the ionization energy. Some other things I just wanted to show you as we finish off here is that here's some data on ionization energy. So you can take one electron, and then you could come in and take another electron, right? So you can see here sodium, right? Sodium has one valence electron. So in order to remove that, it takes this much energy. Okay, if you try to take another one from sodium, because sodium already gave one away, so now it's has its shell of 8 electrons, it's happy. So if you try to take the next one, it's a lot more energy to take that one, okay? All right, so here's magnesium. Magnesium has 2 valence electrons. So again, if you're looking, reminding yourself of what the Lewis dot structures look like, right? Sodium had 1 valence electron, right? So you can remove it, takes not too much energy here, right? But then if you try to remove, because remember, inside those inside electrons, there's already 8, right? And then we would have this 1 by itself. So if you try to go in, like once you take this one out and try to take one of these 8, right, out, it's going to take a lot more energy. It's not going to like that. Where magnesium had 2 valence electrons, so here you can take it with that much energy, here we take it with that one. But again, if you go into its next electron shell here and try to take more, it's going to take way more energy here. So the orange here is just kind of like the valence electrons are already there, and then the blue is like going into the next shell. Okay, it's going to take way more energy. Okay, so just showing you that here, a lot more energy there. Okay, and then I think that was it that I wanted to show you today. So yeah, so just kind of review this note over and over again, and then practice being able to communicate and be able to explain things using all of these new terms in order to describe why the atomic radius is showing this trend here. Why is the ionization energy showing this trend?